Freight transportation is an absolutely essential part of modern life. Maintaining the complex supply chains of raw materials to finished goods requires a seemingly endless amount of hustle and bustle. Millions of tons of freight are moved each day, mainly on trucks and trains, but shipping got its name for a reason, and we still use ships to move a lot of our stuff. One of the main reasons is that it's efficient. In fact, moving a ton of goods the same distance on a boat takes roughly half the amount of energy than it would take by train, and roughly a fifth of the energy it would take on a truck. You can prove this to yourself pretty easily. Even heavy stuff is practically effortless to move around once it's floating on water. Of course, shipping by waterway also has its limitations. It's slow, for one, and not every place that needs goods is accessible by boat. We've overcome this obstacle somewhat through the use of constructed waterways, or canals. Canals and shipping are described in the earliest works of written history. But there's another limitation more difficult to surmount. Water is self-leveling. Unlike roads or rail, you can't lay water up on a slope to get up or down a hill. Luckily, we have a solution to this problem. It may seem simple at first glance, but there's a lot of fascinating complexity to getting a boat up or down in a river or canal. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about locks for navigation. The efficiency of water transportation has a surprising amount to do with how the world looks today. Nearly every major city across the globe is located on a waterway, accessible by shipping traffic. Waterway transportation is weaved into the history of just about everything. So it's no surprise that even since thousands of years ago, humans have sought to bring access by boat to areas otherwise inaccessible. But creating waterways navigable by boats isn't as simple as digging a ditch. Unlike the open sea, the endless and uncluttered surface of water, land has obstructions and obstacles. The topography dips and rises, rivers and ponds get in the way, and man-made infrastructure like cities, roads, and utilities impede otherwise unhindered paths from point A to point B. The quintessential example of this is the Panama Canal, the famous cut through that narrow isthmus, saving ships the lengthy and dangerous trip around Cape Horn. At scale, this seems pretty straightforward. Just cut a ditch from the Atlantic to the Pacific. But the details of what is one of the largest civil engineering projects of the modern world are more complex. One of the most important of those details is that the majority of the Panama Canal isn't at sea level, but actually 26 meters or 85 feet higher. This is due to sheer practicality. Construction of the canal was already one of the largest excavation projects in history. Keeping boats at sea level would require cutting, at a minimum, an 85-foot deep canyon through the peninsula, involving millions and millions of tons of extra earthwork that would be completely infeasible. So, rather than cut the channel deeper, we instead raise the boats up from sea level on one side and lower them back down on the other. And we do this using locks, an ingenious and ancient technology that's made possible navigation on waterways and canals that otherwise could never have existed. The way a lock works is dead simple, and of course I have a little demonstration here to make this more intuitive. For a boat going up, it first enters the empty lock. The lower gate is closed, then water from above is allowed to fill the lock. This is usually done through a smaller gate or a dedicated plumbing system, but I'm just cracking the upper gate open. Once the level in the lock reaches the correct height, the upper gate can be fully opened and the boat can continue on its way. Going down follows the same steps in reverse. The boat enters the full lock, the upper gate is closed, and the water in the lock is allowed to drain. Again, I'm just cracking the gate in the demo, but this is often done through a slightly more sophisticated way in the real world. Once the lock is drained, the lower gate can be fully opened and the boat can continue on. I hope you see the genius of this system. It's a completely reversible lift system that, in its simplest form, requires no external source of power to work, except for the water itself. One thing to notice about a lock is that even though boats can move through in both directions, water only moves through in one. The lock always fills from the upper canal and always drains to the lower canal. This is because gravity, hopefully that's obvious, but it's important to realize that even though we're not using pumps, the energy required to raise and lower boats through a lock isn't necessarily free. Each time the lock is operated, you lose a lock full of water downstream. And sometimes that matters. Canals aren't full of limitless water, and if there's a lot of traffic or the locks are particularly large, this could mean losing millions of liters of water per day. On large rivers, it's usually not enough to worry about, but in some cases this could cause a canal or reservoir to go completely dry. So, canals that use locks need some way to replenish the lost water, or at least limit how much water is lost each cycle. What if there was a way to save the water used to fill the lock and reuse it? On the Panama Canal, the locks use water from Gatun Lake, a critical source of drinking water for the country. During periods of drought, water supply becomes a serious issue. That's why when the canal was expanded in 2016, the new locks included water-saving basins. Like the locks themselves, these basins are an extremely simple and yet ingenious way to limit the amount of water lost each time the locks are filled. Let me show you how this works. On my demo, instead of draining the lock into the downstream canal, I can drain it partially into a nearby reservoir. Then, when the time comes to fill the lock, I can recycle the water from the basin, also called a side pond, to partially raise the level. Of course, I still need to use water from the upper canal to fully fill the lock, but it's less water than I would have used otherwise. In fact, if the water-saving basin is the same area as the lock, you can save exactly 1/3 of the water. The reason again is gravity. Water doesn't flow uphill, it always has to be going down. To be able to save water, you need a volume within the lock for it to come from, a lower volume for it to drain and wait in the side pond, and finally an even lower volume within the lock for the saved water to go. That means the best you can do with a single basin is to save 1/3 of the water that would otherwise be lost. But it's possible to do better than this. One option is to have the water-saving basins have a larger area. Imagine an infinitely large basin so that no matter how much water drains into it, its level never rises. In this case, you could drain the upper half of the volume of the lock into the side pond and then use that water to fill the lower half of the lock on the way up. So the area of the basin is important, with the larger area providing a greater water-saving benefit. The other way we can do better is to have more basins. Notice on the diagram that the bottom 2 volume divisions are lost each cycle. When the lock drains, each volume division moves from the lock to the side pond 1 division below, except for the bottom 2 divisions which are lost downstream. That water can't be stored in a side pond because the pond would have to be at or below the bottom of the lock. And when the lock is filled, each side pond fills the volume of the lock again 1 division lower. The top 2 divisions can't be filled from a side pond, so they're filled from the upper canal. It's pretty easy to see why more basins equals smaller divisions, and why that equals less water lost each cycle. Of course, for both the number of ponds and their area, there are practical limitations like how much land is available and the expense of all that plumbing. So you have to balance the value of saving the water in the locks versus the capital and ongoing expenses of constructing and operating these basins. That's made a lot easier with a pretty simple formula to calculate the ratio of how much water is used with side ponds versus without them. The new locks at the Panama Canal each use 3 basins, which are about the same area as the locks themselves. Plugging in 3 for the number of basins and 1 for the lock to basin area ratio, you can see that the new locks use only 40% of the water that would be required to operate without the basins. That's pretty impressive and definitely seems worth the cost of the basins. But it's not the only example of this. Another lock in Hanover, Germany has 10 basins, reducing the lost water by about 3/4, although the tanks are underground so they're harder to see. I've been talking about freight transportation in this video, but people use boats for all kinds of different reasons, and in the same way, there are all kinds, shapes, sizes, and ages of locks across the world. In fact, there are a lot of canals where you can operate the lock yourself. They're also not the only way to move a boat up or down, but that's a topic for another video. Next time you see a lock, consider where the water comes from, and keep an eye out for side ponds that help save a little or a lot of it for the next time. Hey, very quickly I just want to say this video was supported by viewers like you through Patreon. YouTube's not a full-time gig for me, and there are quite a few costs that go into these videos, from materials, digital assets, equipment, and help from professionals. Sponsors and ad revenue come and go, but the supporters on Patreon are the ones truly making it possible for me to put out a video like this once per month in my spare time. So huge thanks to them. If you like this video, I hope I earn your subscription. You can also keep up with everything I'm doing in my monthly newsletter, link below. As always, thank you for watching, and let me know what you think.